So 20 years ago, as many as 94% of Year 11 and 12 students were enrolled in science subjects at school. By 2010, that dropped to 51%. The number studying physics in VCE dropped from 22% in 1990 to just 15% by 2004. Young people are losing their enthusiasm for science, and it's not hard to figure out why. Science at school is often dry. Students who should be doing, exploring and thinking are instead rote learning endless formulae that seem far removed from their reality and experience. Now, this is a serious problem for a couple of reasons. Firstly, the Chief Scientist of Australia points out that innovation, especially in science and technology, is at the crux of economic development. Australia has fallen from 5th place to 20th on the Global Competitiveness Index since 2001. Engineering Australia reports that there is a shortage of 20,000 engineers right now. We need more students to take up scientific careers. Secondly, we want citizens with scientific and critical thinking ability. As a society, we need people to be able to look at a concept and critically evaluate it, to ask, how does it work? What are its flaws? And where is the evidence? Consider the current debate on climate change, one of the greatest challenges facing us today. Now, I suspect that if everyone had an understanding of scientific process, of what constitutes evidence, and if we could critically evaluate the opinions and motivations of the shock jocks and the vested interests, it would actually be a very different debate. Asking someone if they believe in climate change would no longer be a common question. Now, science can be broadly split up into the natural sciences, such as biology, zoology and genetics, and the physical sciences, maths, chemistry and physics. Now, the natural sciences are doing okay. Science enrolments at university has gone up by 30% in the last 10 years, compared to 33% uni-wide. And almost all of this growth is in biology and behavioural sciences. However, physics seems to be increasingly failing to capture the interest of students. Teachers are doing the best they can with a school curriculum that is crowded and often encourages the memorising of mathematical formulae. It's no wonder people think that physics is difficult and boring. Even in first year uni, students having to take a semester of physics to get into medicine or veterinary science often see the subject as something to get through then get out. And this is despite our attempts to make kinematics more relevant by asking students to plot the trajectories of bodily fluids. I wish I was joking. Now, this is really disappointing for me because, well, physics is actually totally badass. For the next few minutes, I would like to share with you a couple of the big ideas and experiments in physics that inspire me every day. Now, the first is called dark matter, but before I can tell you what it is and why it's awesome, we first need to talk about normal matter. Now, you've probably heard of protons, or neutrons and electrons. These are the tiny little particles that make up atoms and molecules, which make up you and me, the stars, the Earth, all of the galaxies that we see in the night sky. Pretty much anything that you can think of, it's made of normal matter. Now, here's where it gets interesting. All of that normal matter, that makes up just 4% of what's out there in the universe. Only 4%. The rest is made up of stuff called dark matter and dark energy. And I don't mean that our bit of the universe is made up of normal matter and somewhere else there's these big clumps of dark stuff hanging around. Dark matter is actually all around us. It's in the sun, it's in the Earth, and it's holding our galaxy together. Dark matter is called dark because we can't see it. We've never observed it directly. We don't know what it's made of or what it does. We know it exists because the universe is 5 times as heavy as it should be. And dark energy, the rest of the universe, we barely have a clue. For thousands of years, we've been studying the world around us, and we've only just recently realised that that's just the tip of the iceberg. Now, you may have heard of the Large Hadron Collider at CERN. That's the experiment that's going to create a black hole and destroy the Earth, but probably not. Now, the LHC is a ring of magnets, 27 kilometres around, used to accelerate protons to more than 99% of the speed of light. In case you're not sure, that's pretty damn fast. Those protons are going around that 27 kilometre ring 11,000 times every second. And what's even cooler is that we can then smash these protons into each other. Now, to put this into perspective, this is like firing 2 needles at each other from 10 kilometres apart and scoring a direct hit. Now, the reasons we do this, apart from the incredible fact that we even can, are to answer some pretty basic yet extraordinary questions. Questions like, why are some particles heavier than others? What was the universe like straight after the Big Bang? Do extra dimensions exist? And what actually is dark matter? This is Super Cameo candy, a massive tank in an abandoned mine in Japan filled with 50,000 tonnes of ultra-pure water. The walls are lined with 13,000 individual detectors. Super Cameo candy is looking for neutrinos, the smallest, lightest particles that we know, and the universe is absolutely teeming with them. If you can imagine a pea sitting on the palm of your hand, 65 billion neutrinos are whizzing through that pea every second. Neutrinos that were created in the centre of our sun. These are the particles that recently caused a stir when some physicists suggested that they might be travelling faster than the speed of light. Everyone got a bit excited and started talking about Einstein's rules being broken and what might be next. Now, unfortunately, some faulty wiring turned out to be to blame, but the question, what if, remains. This experiment is called Ice Cube, which is kind of fitting because it really is just a giant cube of ice, a whole cubic kilometre in fact. This is the biggest neutrino detector in the world, buried more than 2 kilometres under the ice, in Antarctica. We need such large detectors because although neutrinos are so numerous, they're also extremely hard to detect. Now, unfortunately tonight, I don't have time to explain how we can make a Pac-Man ghost out of electrons, or move matter from one place to another without it being in between. The idea that an electron can behave as if it's in 2 places at once is something that you're going to have to go home and look up yourselves. Now, what can we do to make physics, and more generally the sciences, more interesting, appealing and inspiring to students? The Academy of Science suggested rewriting the science curriculum. We could make it more relevant to students, as well as leave space for encouraging curiosity and critical analysis of results. They also recommend supporting our teachers better, with better pay and further training. Finally, researchers also need to get better at communicating science to the public and telling our stories to the media. We need to promote the idea that science is still relevant, it's still interesting, it still is a viable career, and it is something that young people can become involved in. Thank you.